So as we've been doing, we're just kind of doing some reviewing of the different chapters that we went over. Hopefully it'll be helpful for you. Kind of hitting the main points out of those chapters, sort of the main formulas and stuff that we learned, and equations. And we last time talked about, I think, the first couple of chapters through acids and bases. So we'll just kind of pick up from there. Obviously, we'll do this for a little bit here today. We'll take a break and then we'll go and take the exam around the start of lab, about 1-ish. And then that will wrap it for today, leaving us, I think, just one more day on Wednesday to go. And then that will be it for the semester here, I guess. All right. So as I mentioned before, we're talking about, we got through acid and bases in that chapter. So that then led us really to sort of the next chapter, which sort of built on those topics. And that was, I believe, chapter 15. And chapter 15 was sort of a really big chapter, as we talked about when we went through it. It had really a lot of the big topics, the kind of more difficult topics for a lot of students in this class. It really revolved around really two big topics, which were buffers and titrations in this chapter. And so first off, we sort of started talking about the idea of really, what a buffer sort of is and sort of how it works and stuff like that. But really the basis of all that was the idea of this idea of a common ion. So the presence of common ions affect things. We've seen it affect things in some different areas along the way, but the presence of a common ion definitely does affect basically the acid, weak acid, or base, basically ionization. So basically the presence or having that common ion there, and basically the idea there is it's really just Le Chatelier's principle sort of kicking into effect. So as we talked about, if you had something like acetic acid, it normally would break apart into H plus and acetate. And in water, that's a big space there between this. We'll make the three bigger. In water, it obviously would break apart in this sort of equilibrium. If we then put it in, in a solution that also contains, say, sodium acetate, the acetate part here is really the common ion. And based on Le Chatelier's principle, what that's going to do basically is force the equilibrium basically back to the left in this case. And by doing that, what that essentially will do is keep this weak acid basically still together, and it won't break apart as much. It won't dissociate as much. And the result of that, in terms of, say, something like pH, as we talked about, is essentially because it's kind of forcing the equilibrium to the left, we end up having less of the H plus being produced. And remember that it is that H plus that really affects the pH of that solution. So we actually will see, in the case, say, of acetic acid, in a common ion sort of effect, we typically will see perhaps the pH being a little bit higher than it would be if it was just acetic acid by itself. Again, pushing that equilibrium back to the left, keeping less of that H plus from basically coming off, less H plus in the solution, really less free H plus in the solution, means that, our pH is going to be affected by that because, again, as we talked about last time as well, right, as the H plus goes down, for example, OH minus goes up. And the result of that is your pH goes up and vice versa, right? There's sort of that opposite relationship between the H plus concentration and the OH minus concentration, and really the pH as well. pH will go down in that particular case. So really the basis of the common ion is really what a buffer is, right? And a buffer, as we talked about a number of times, a buffer is a solution that will maintain the pH even if you add some acid or base to it. So does it maintain the pH like perfectly? There's absolutely no movement, and the answer, as we talked about, is no. There is some movement, a little bit up, a little bit down, but what we're talking about here is we won't see giant changes in the pH or big swings in the pH when you add acid or base to it. And the reason for that is because of what a buffer is made up of. It's made up of basically one of two combinations: a weak acid and the salt of its conjugate base. Or you could have a buffer that is made up of a weak base and the salt of its conjugate acid. And again, in a buffer solution, they are both present to begin with. So it's not like you're sort of adding them one at a time. You kind of can basically dump both of those things into a beaker in the right proportion, and you would have a buffer at that point. Remember that a buffer cannot be made up of a strong acid or strong base because they will not set up an equilibrium. And you need that equilibrium, kind of like what I wrote right here. You need that equilibrium to establish, to keep in solution a good amount of the acid part of the, say, the buffer and the base part of the buffer, basically. So you need both of those guys to be able to kind of set up into that solution. Now, if you have a strong acid or a strong base, you will not get really either the acid part or the base part to stay in solution because those things 100% break apart. They cannot be considered a buffer. And again, that's not to be confused with a situation that we talked about before, and I think we maybe even saw in lab as well, that you can definitely make or produce a buffer from a reaction of a strong acid with a weak base or a strong base with a weak acid. But it's not really considered a buffer until pretty much that reaction is complete. And at that point, the strong acid and strong base will be pretty much gone at that point, used up completely to kind of produce a buffer. So you can sort of make a buffer, produce a buffer, I guess is a better way of putting that, by doing a reaction of a strong acid, again, with a weak base, or a strong base with a weak acid. But again, that strong acid or strong base that's in that reaction is not the buffer. The buffer is basically the result of that chemical reaction when it's all said and done. Also really important, right, with a buffer is that it is not necessarily a neutral solution. You can make a buffer at any pH you want. The important part there is it will basically maintain that pH. May go up a little bit, up or down, but no big jumps in pH. So really, how does a buffer work? Well, a buffer works because, as we talked about, you basically have those sort of two components in it. So when you make a buffer, you have the acid part and the base part there. And when you add acid to the buffer, it will react with the base part. But as we also saw, a very interesting sort of aspect of buffers is it will actually make the other part of the buffer. So you'll kind of use up some of the base part of the buffer, but you will kind of regenerate the acid part, and vice versa this way. If you add base, it will react with the acid, but it will regenerate some of the base part of the buffer as a result of that reaction. So this makes two sort of interesting things about a buffer. One is it's in a sense sort of regenerating part of the buffer, but it also illustrates the fact that there is a sort of buffer capacity, right? There's a limit to how well a buffer could work because, again, if you just got to look at either of these diagrams, if we add too much acid, we will continue to basically burn up the base part of the buffer until it will no longer be able to really effectively work as a buffer. And at that point, you would see a big change in pH. And same thing here. What's really sort of the important part and what really allows you to know, how affected your buffer can be or how effective your buffer can be is really the moles, right? It's really the moles of the acid part and the base part that's important, because these are really the guys that do react when you add more acid or base to a buffer. And if you add an acid or base to your buffer where you're adding way too many moles, you will basically kind of burn through your buffer. So for example, as I think we maybe demonstrated one time, let's just say we're going to have a buffer of acetic acid and we're going to add some, say, sodium hydroxide to it. And when we do that, the sodium hydroxide will react with the acetic acid. It will produce sodium acetate, which is the other part of the buffer, and some water in this particular case. Now, if we started, say, with 4 moles of our acetic acid and 4 moles really of our sodium acetate, and we decided we grabbed way too many moles of this guy, and we ended up adding, say, 6 moles of our sodium hydroxide to this buffer. When we add that 6 moles of the sodium hydroxide, what happens is now we really don't have enough moles of our acid part of the buffer to use up our base. And our acid part will now become like the limiting reagent. This guy will be like the excess reagent. And what will happen if we just kind of go through the change part actually is going to be the moles of the acetic acid here that would be used up. And the result of that is when we do reach equilibrium in sort of a buffer reaction like this, we have nothing of that. We would have 2 moles of this guy and like 8 moles of that guy. But a couple important things we could see is as a result of this ice table is we obviously have at the end sodium hydroxide, and in this case of this example, sodium acetate. That again, although there's 2 things left over, these 2 things are not a buffer at this point. You basically have 2 bases. This is a guy that's going to go through hydrolysis and produce OH minus. This is a strong base, which is pretty much just going to go for a swim and quickly produce OH minus. So the result of doing something like this, where maybe you add the wrong amount of sodium hydroxide or your buffer is really not made to the correct sort of molarity or moles, what's going to happen in this sort of situation is at this point, you are pretty much just dumping in a bunch of hydroxide. The major contributor of hydroxide probably at this case is the sodium hydroxide. And basically you would expect a pretty big jump in pH in this case. And that's what we sort of talk about when we talk about sort of buffer capacity or effectiveness. We did that one experiment where it did the graph, and at some point you saw really quickly sort of the diluted buffer broke apart and couldn't hold the pH as long as the more concentrated buffer. And again, that's why it's really important when you're making a buffer to make sure that you not only sort of make it in terms of the correct pH that you're looking for, but you obviously do want to make it appropriate in terms of the moles to handle whatever acid or base that you're adding to. Any questions on that there? So in a normal sort of buffer situation, what happens is, right, when we add something like sodium hydroxide or a strong base or a strong acid to it, we do have sufficient amount of moles of our buffer to handle it, and we don't see that big jump in pH. So, normal situation, if you sort of make your buffer correctly and you do the same reaction, again, you get the same sort of outcome. But the difference is you would be left with the buffer when it's all said and done. And most importantly, how come a buffer really doesn't sort of have these big jumps in pH? As we talked about as well, it's really what you don't see here on the product side. We don't see any free OH minus being produced. So because there's no free OH minus being produced, the concentration of H plus remains relatively constant. And again, the pH also remains relatively constant. Same thing would happen if we added an acid to this buffer. Again, the sodium acetate would react with the acid. It would produce our acetic acid, like we would anticipate, and some sodium chloride. And same thing here, as long as we made our buffer sort of correctly and what we're adding is okay. Why it doesn't really jump pH again is something we actually don't see, and that's because there's no free H plus produced. So there's no free H plus produced here, which obviously keeps that concentration relatively constant. and obviously would keep the pH relatively constant as well. So ultimately, a buffer is able to handle, in a good situation or sort of a correctly made buffer, is able to handle addition of acid or base to it because it has an acid part and a base part. And ultimately, it prevents the formation of free H plus or free OH minus. And that ultimately is what, makes pH basically change a lot, is how much H plus or OH minus that you have freely floating in that particular solution. We saw an equation that obviously relates to this. And by the way, before we move on from that, as a reminder, this is what an ice table should look like, right? When we add volumes like we would be doing here, whenever the volume is changing, we want to make sure we do our ice table in moles. And again, at the end of that first ice table, you can convert back to molarity, which is a very good move as well. So we saw that aspect of it in terms of ice tables and moles, definitely starting here with our buffers. So when we add acid or base to a buffer, definitely want to do that ice table and moles. We also saw it again in titrations as well. There is an equation that really does go with buffers, which is the pH is equal to the pKa plus the log of the base over the acid. And that's our Henderson-Hasselbalch equation. And remember that the pKa here is equal to minus the log of the Ka. This equation, as we've seen, can be used and really should be used for only a buffer situation. Again, you don't want to use it on every situation that you have. Just if you're sure it's a buffer, you could do it. Why is this equation sort of helpful? It's helpful because it can allow you not to have to do an ice table. So if you perhaps do a reaction like we did before, you have two options as to how to sort of get to the pH. So if we just look at that same reaction here, and let's just say we added everything sort of okay. So let's just say we had initially our 4 moles. Let's say we only added 2 moles of this guy, 4 moles. Change would be -2 plus 2, which means we would end up with 2 moles of this guy, 0 of this guy, and 2 moles of this guy. We can convert back to molarity here. And remember, at this point, you have two options. You could do another ice table to get to the pH. So you could do an ice table, which would be usually based off of the weak acid. Using your above molarities from above. And obviously solve for X. This would be more of an X table. So like minus X plus X plus X. And molarity minus X, X, and molarity minus X. So you would solve for X here, right? X would be the H plus concentration, and that would get you to your pH. Alternative to that, you can at this point recognize this as a buffer. You can go just right into your Henderson-Hasselbalch equation at this point, which is sometimes a little bit easier, maybe less room for error and stuff like that. So, you do have sort of two options when you're dealing with buffers as to how you want to get to the pH. It sometimes will require 2 ice tables if you take the strictly ice table approach. If you do sort of the Henderson-Hasselbalch equation, 1 ice table and the Henderson-Hasselbalch equation. Remember, though, that this would be a situation where we're adding something to it. If you're not adding something to it and you just want to find the pH of a buffer with no addition, you also have really those two options. You could go ice table, and you can go with the Henderson-Hasselbalch equation as well. Remember, though, if you're doing an ice table, you want to make sure that you have starting amounts on both sides of that arrow for your acid and your base part of your buffer. So that's an important part that sometimes missed when people do an ice table. They forget to do the concentration or initial concentration of the other guy, which means they're really not doing a buffer. They're just doing either a weak acid or a weak base. So again, if you're not adding anything, you can ice table one ice table with concentrations, the initial concentrations, or you could go right into the Henderson-Hasselbalch equation and get to the pH. Any questions on that there? In addition, we talked about a couple other sort of similar equations that we kind of talked about in the sense that, you know, you can use them if you want to, but there's maybe not such a great benefit of using it. And it is one that does look at the POH, which is the pKb plus the log. And remember that this flips when you're doing it, acid over base versus base over acid. pKb is just like you do the pKa minus the log of Kb. But there is a nice relationship between those two that if you take the pKa plus the pKb, it does equal 14. Now, you absolutely could do this for like a basic buffer, and sometimes you'll see people use these equations for the basic buffer, but a reminder that most of the time you're looking for pH. So it makes sense to really just kind of go into this equation because you could use it for really acidic, basic, or neutral buffers. It really doesn't matter. You know, as long as you have really the pKa value in the base over the acid. So sometimes people will use the guy on the right there for more basic buffers, but then you got to obviously at the end, most likely do the 14 minus the POH again, because you're usually looking for that pH value here. Remember that those values do run opposite of each other, the pH scale and the POH scale. So, you know, most of the time people go with this guy here. We could also use the Henderson-Hasselbalch equation to help us figure out sort of, you know, how to make a good buffer or pick what we should be looking for in terms of producing a buffer at a specific pH. So if we just think about sort of this part of it, if we make a buffer and use a pretty effective buffer is one where, you know, the concentrations of the acid part and the base part of the buffer are relatively equal to each other, or, you know, have about the same amount of each of those guys. And if you do that and you look at the Henderson-Hasselbalch equation, that essentially would turn this back part of the calculation into like the log of 1, which is essentially 0. And that means that when you're trying to kind of choose a weak acid or a weak base to make your buffer firm at a specific pH, usually we're looking for somebody that has sort of a pKa value that's plus or minus 1 of your desired sort of pH. So for example, if you looked at something like ammonium has a pKa value of like 9.25, that would be a really crappy choice to make a buffer at a pH of like 4. Again, it's pretty far away. That's probably a bad choice. Acetic acid, on the other hand, has a pKa value of 4.74. That would be a much better choice to pick to make out your buffer. You could also use the Henderson-Hasselbalch equation to figure out the ratio of base to acid that you would need to make a buffer at a specific pH. So it's a very useful sort of equation. Any questions on buffers there? In addition, we then started talking about titrations, and obviously titrations, a pretty big topic. And we use a burette. We add sort of a known solution to an unknown solution. And this is definitely a situation where, you know, when we do sort of ice tables, usually that first one does need to be in moles, because pretty much we are constantly adding volume here, which means constantly the molarity is changing. So we definitely want to do those things in terms of moles. We talked about a few different types of specific titrations. We talked about a titration of a strong acid with a strong base. And in this setup here, we have sort of our strong base up in the burette, and the beaker or flask is our strong acid. And we basically would be adding our base to our acid in this case. This yields us a titration curve that we've seen. and probably pretty badly drawn here, but I'll give it the old try here. Volume of base added, and we get this sort of S type of curve that occurs here. And all sort of titration curves that we talked about, there really is sort of four distinct parts along the curve. There's sort of the first part, which is, before you start the titration. Somewhere there's the equivalence point, and in that sort of second region is actually before the equivalence point. Third region would be at the equivalence point, and a fourth region would be after the equivalence point. And remember that the importance of the equivalence point, especially when you're sort of thinking about titrations, is to remember sort of the basic definition of what it means when we reach the equivalence point. When we reach the equivalence point, that is basically an acid-base titration where the moles of the acid equals the moles of the base. So that also can help you as you're sort of doing calculations if you're not sure sort of where you're at in terms of the titration. Figure out, am I before the equivalence point? Am I after the equivalence point? Am I at the equivalence point? And that's sometimes very helpful for the calculations. In this sort of situation, before we start the titration, sort of at step number one there at before, we basically only have a strong acid, which means that because it's a strong acid, that pretty much will break apart into H plus and something else. And that pretty much means that we have the concentration of H plus, which means we could simply go right into, in most cases, the pH equation to figure out the pH at that point. So that's a really nice thing about doing this type of titration, especially at the beginning. There's not much calculation sort of happening. We already obviously know the concentration. We don't have to worry about moles or anything like that because we haven't added any sodium hydroxide in this example yet. So we could just go straight into it. When we get to sort of step two here, in terms of the titration, we are adding some base. So it does require one ice table that needs to be done in moles, obviously, because we are adding volume. And once you do that, what you'll be left with is still your strong acid because it has not reached the equivalence point. So up until this point in this titration, the base that you're adding is essentially the limiting reagent going to be used up. Once you have your strong acid really concentration, that will then allow you obviously to go right into your pH equation at that point, and you can figure it out. So remember, this is a situation, as we talked about many times, you want to do that first ice table in moles, but you definitely want to convert it back to molarity and then obviously continue on. At the equivalence point, that is when our moles of, again, our acid will equal our moles of base. That means that in this particular type of titration, and probably others as well, but in this particular type of titration, you'll be left pretty much with a salt left over. And the importance of that salt is that it obviously does come from a strong acid or strong base. So as we talked about with hydrolysis, that means that is going to be relatively weak or a neutral salt, which means there's really no calculation here in this type of titration at the equivalence point. We would expect that the pH would be a pH of 7, which is neutral. Again, no matter what combination that you put together of a strong acid or strong base in a titration like this, you will always end up with pretty much a neutral salt. And there's really no calculation that's sort of needed in that case, which is kind of good. And that leaves us with, in our titration curves, which is something different for a lot of people in this class, we usually, in most titration situations that you probably talked about previous, that's pretty much where we stop, or kind of the goal of where we want to stop. But we do continue on in this type of situation. And what happens sort of at that fourth step is you're really adding excess base at this point. And you do need to do a 1 ice table, also again in moles. And what you'll be left with is a strong base. And because it's a strong base, you'll be able to figure out the concentration of the OH minus, remember, because it's a base, which will allow you to calculate the POH, and then you could calculate the pH at that point. So, in this type of titration, we see a couple of things that are common throughout a lot of titrations, but we can do ice tables, and you should do ice tables whenever you're sort of obviously adding throughout the titration here. But you do want to convert it back to molarity. And remember, understanding sort of the equivalence point situation here allows you to use your ice table, like I mentioned before, to really figure out where you're at. Remember that, sometimes they don't tell you what the volume is at the equivalence point. So there's multiple ways we talked about that you can figure out something like that. The simplest way is sometimes just using like the dilution equation. And again, remember, this works for a 1-to-1 relationship between your acid and base. And you can kind of do that where, M1V1 is your acid information, M2V2 would be your base information. You could find how much volume you would need to get to the equivalence point. Also important, as we talked about, that volumes are not sort of additive in that sense. When you have a problem where it asks what the pH is at multiple sort of spots along the way, you don't just keep sort of adding one spot to the next. For example, if I said what's the pH after 5 milliliters was added, what's the pH after 10 milliliters was added, what it means is you opened it up and stopped at 5 milliliters. For the 10 milliliters would mean you started at 0 and opened it up and stopped at 10 milliliters. So make sure you don't add that. The other couple of important things we talked about is obviously we can signal the equivalence point by using something like an indicator. And what we typically do see at the equivalence point is this situation here. We see a lot of verticalness that occurs as we approach the equivalence point. We typically see a jump in pH to the equivalence point. We also typically see a jump in pH after the equivalence point. But the volume for the equivalence point is oftentimes very much in this vertical area, which, as we talked about, if you're doing sort of a titration, if you're being very careful about how you're titrating, you're not adding a lot of volume at once, you can, even if you kind of indicator wise, it goes really dark pink, for example, for using phenolphthalein. If you were very careful and you miss it by a drop or two, overall volume difference will probably not be that much. If you're not very careful, you could get that same pink color, but actually end up like way over here, which obviously would be a very big difference between the equivalence point volume and stuff like that. So we talked about the idea as to why a lot of times people have done titrations before, perhaps, and they usually very commonly say, hey, I just added one drop in, like, for example, my phenolphthalein indicator went like colorless to like super dark pink. And it's because when we approach that equivalence point and pretty much most acid-based titrations, it goes fairly vertical, which means you don't have to add a lot of volume to change the pH a lot. And remember, that's pretty much how indicators work. They work off of a pH range. So even though you added just a little bit, it maybe went from a pH of 8 to like, a pH of like 10. And that's going to show a very big color change in the indicator, although you could still be, within the realm of the volume of the equivalence point. If you're careful, you could be outside that realm if you were not careful. Any questions on this type of titration? We also then talked about another type of titration, which was a weak acid with a strong base here. So we talked about a weak acid with a strong base. And again here in the burette, our strong base. And obviously down here, our weak acid would be better way, right? That our weak acid. There we go. And again, it does yield you that similar type of looking curve. Volume of base added. Again, give it the old, go that way with it there. See how I did? Yeah, not too bad. All right. So just like the previous one, we're going to have, it's a little lopsided there. We will have the same sort of 4 points. We got sort of that initial point. We got that before the equivalence point. We have at the equivalence point, obviously, which is number 3. And obviously after the equivalence point here, which is number 4. So the calculations involving these guys are a little bit different than the one we just talked about. Again, really because we're starting with a weak acid. So initially, because it's a weak acid, we haven't added anything. We would do an ice table for that weak acid, like a Ka problem, basically. We would solve for X. X would equal the H plus concentration, which would then allow you to get to a pH. So again, we don't have to do moles or anything like that. Again, we haven't added anything, so we can simply take the concentration of the weak acid. That will sort of give us our opening pH here for this particular titration. Now, once we do hit sort of the second part, just like in the previous one, we do need to do an ice table. And at number 2 there, we need to do at least one ice table. It does obviously have to be in moles. What you're going to be left with after that ice table is you're pretty much going to be left with a buffer. So you'll have really the concentration of the weak acid, and you'll have the concentration of the conjugate base. And at that point, right at the end of the table, you should convert back to molarity. You have the 2 options that we just spoke about. You can either do another ice table if you wanted to, or you can use obviously your Henderson-Hasselbalch equation. They both should again yield you pretty much the same deal, because remember at this point in the titration, you pretty much will have a buffer, sort of the buffer region that occurs. And again, you have sort of 2 options. So either 2 ice tables or at least 1 ice table, really to get those concentrations really of your buffer. And it will be an acidic buffer. You could go into the Henderson-Hasselbalch equation. Any questions on that one there? When you get to the sort of third point here along the way, again, our moles of our acid will equal our moles of our base. And basically what that means is you will need to do really an ice table. When you do that ice table, you will find, just like we saw before, you will have a salt left over. The difference, though, is this salt came from a weak acid, which means because it came from a weak acid, it will go through hydrolysis. And you will need to do a second ice table, which is basically a hydrolysis table for that salt with water, right? And we would expect it to be basic at the equivalence point. It'll be basic at the equivalence point because the production of OH minus is being made. So at the equivalent point, much different than obviously the one we talked about before there, where you just write 7. You do have to do several calculations here. Basically a double ice table situation. Really the first one is to figure out what is the concentration of this salt. That's basically what that's for. Second one is using that concentration and doing a hydrolysis reaction with water, and it will again allow you to get to that pH. Also a reminder that probably somewhere along there, you might not have the right K value. You might need to do the Ka, Kb is equal to Kw and sort of figure out, what the pH would be at that point. And lastly, at the 4th step there, just like in the previous one, you're pretty much just adding a lot of excess, I would say sodium hydroxide will go base generically. So at this point, you've reached the equivalence point. You pretty much have used up all the acid that you started with, and you're pretty much just now dumping in there a bunch of excess base. That means that you do need to do an ice table, Purpose of the ice table is really to figure out the concentration of your strong base. Once you have the concentration of your strong base, that's going to give you your hydroxide concentration. That will get you to your pOH and then to your pH in that case. Any questions on this type of titration here? And then lastly, in terms of titrations, we talked about a third titration, which is a strong acid and a weak base titration. And in a strong acid, weak base titration, pretty much the same deal. A little bit different though. We are actually adding the strong acid. And down in the burette there is our weak base. And in this particular case here, going to yield us a titration curve that looks a little bit different. It's actually going to come down and around. Free-handed it there. But we'd still have the same 4 points along this titration curve as the previous one. And again, going through this, we would obviously have just the weak base to start with, requiring you to do an ice table. It's really a KB problem. When you do that and you solve for X, it will equal the OH minus concentration, going to get you to the pOH and then to the pH. Remember, you could just use the molarity there as you have not added anything to it. At number 2 along the way here, we also going to need to do an ice table. The result of this is much like the last one. This one does need to be in moles, which you then go to molarity at the end of it. And at the end of it, you will be left also with a buffer here. So this is a buffer region as well. The difference is you'll be left with a basic buffer. So when you do that ice table, again, you'll get the concentration of both parts of your buffer. And you have the same 2 options. You again can do a second ice table to get to the pH, or again, you could use your Henderson-Hasselbalch equation here to get yourself to the pH. So kind of similar, except there's going to be basic coming down from a high pH. Again, a high pH because we're starting with a base and rolling our way down. At number 3, also very similar to the last one, we would end up with basically one ice table here. Again, done in moles, converted to molarity at the end. And at the end there, you will be left with a salt. The salt, just like the previous one, going to be doing some stuff because it does come from a weak base, which means it will go through hydrolysis with water. Maybe hydrolysis with water. Going to result in the production of H3O plus, which means we would expect it to be acidic in this case at the equivalence point. Going to require obviously a second ice table. That's basically a hydrolysis table. And obviously you should get that acidic pH. Just like the previous one, might need to use obviously in this case that Ka, Kb equals Kw sort of situation, just like before, as you probably will have the wrong value given to you in this titration to use for that calculation. At 4, we pass the equivalence point. So in this case, we're actually just adding excess acid here in this case, our H plus. So you do need to do an ice table in moles, then convert to molarity, and what you'll be left with is basically a strong acid. Strong acid means that you have the H plus concentration, which means you should be able to get yourself to the pH at that point. Any questions on this type of titration or titrations or buffers in general here? Okay, so that was a good